So hello dear students, in the today's lecture we will study about potential barrier of finite width and height, that is tunneling effect. Let us consider a particle of energy E, which is less than the height of the potential barrier, is incident on the potential barrier. And the potential barrier is given by whose potential is equal to 0 for x less than 0, is equal to V naught for x greater than 0 less than a, equal to 0 for x greater than a. We term these various regions, this region as region 1, this as region 2, and this as region 3. And we try to depict the potential barrier in the form of a graph. This is the origin, and this point is x is equal to 0, and here we take the potential and the value is V naught, and when x is less than 0 the value of potential is 0 and x is equal to 0, it is V naught. This region is x is less than 0. At this point is x is equal to a, then this region will be x greater than a. Then value of the potential will be equal to V naught in this region, and thereafter it will be 0. So this will be a step potential. And our particle, it is incident on it. Particle is having energy E less than V naught. This is incident particle. So now we will discuss the various options. First is classical view. How classical mechanics deal with this kind of problem. So as energy of the particle is less than the step height, so particle cannot penetrate the barrier. Into region 2. The possibility of penetration as the energy of the particle is less than the step height, then the particle cannot penetrate into region 2. No possibility is there classically. And it will be reflected back at x is equal to 0. Now we come to quantum mechanical view. The quantum mechanical consideration of the same problem give us different results. So quantum mechanically we will have to solve the Schrodinger wave equation. So according to Schrodinger wave equation, in region 1 V is equal to 0. So this equation it will reduce to, instead of psi we use psi 1 is the solution of the Schrodinger wave equation in region 1. So we designate it with psi 1. So if we put so it will be its solution is given by psi 1, which is equal to a e the power iota k1x plus b e the power minus iota k1x. So we term it as this as equation number 2, this as equation number 3. So now we solve the same Schrodinger wave equation in region number 2, and in region number 2 v is equal to v naught, and the solution it will be psi 2. So we can write it like this. So it can be termed as so if we put k2 square, the equation will reduce to so we term it as equation number 5, and its solution is given by so as the solution exists for the wave function in region number 2, so particle can penetrate the potential barrier, but classically it was not allowed, but according to quantum concept it is allowed. So now we move to region number 3. Here potential is equal to 0. The solution will be like k1 square psi 3, it is equal to 0. So we term this as equation number 7, and its solution is given by but as there is no boundary beyond in region number 3, so no reflection can take place in region number 3. As there is no reflection, so this term, it will be neglected. So the solution in the third part will reduce to this, and we term it as equation number 9. So now we have all the three solutions in different regions, and now we will apply the boundary conditions to solve these solutions. So now apply boundary conditions. So number 1, psi must be finite and continuous at x is equal to 0. So it means psi 1, it will be equal to psi 2 at x is equal to 0. So when we substitute the value of x0 in psi 1, so this is our psi 1. When we substitute x is equal to 0, so e raised to power 0 is 1. So which will give us a plus b. Similarly in psi 2, it will give us c plus d. So we mark this as equation number 10. Similarly, psi must be finite and continuous at x is equal to a. So psi 1 at x is equal to a should be equal to psi 2, sorry, it will be psi 2 and psi 3, because it is a boundary separating region 2 and 3. So substituting the values in psi 2, x is equal to a, in this formula it will be c e raised to power minus k2a plus d e raised to power plus k2a, it is equal to f e raised to power iota k1a. We mark this as equation number 11. Now for the derivative, boundary value condition is d psi by dx must be finite and continuous at x is equal to 0. So x is equal to 0, boundary is between the region number 1 and 2. So derivative of first function and psi 2 function with respect to x at x is equal to 0 should be equal. So when we take the derivative, at x is equal to 0, at x is equal to 0. So when we substitute x is equal to 0, e raised to power 0 is 1, iota k1 is common, so it will be a minus b, and here minus k2 is common, it will be c minus d. So here a minus b will be equal to minus k2 upon iota k1 c minus d, and minus can be written as iota square, and one iota cancels, so a minus b comes out to be iota k2 upon k1 c minus d. We mark this as equation number 12. Fourth boundary condition is d psi by dx must be finite and continuous at x is equal to a. So it is d psi 2 by dx at x is equal to a should be equal to d psi 3 by dx at x is equal to a. So now we take the derivatives. c minus k2 e raised to power minus k2a d k2 e raised to power k2a we will substitute the limits later on. So firstly I write here x at x is equal to a f iota k1 e raised to power iota k1x at x is equal to a. So this is the derivatives of the wave functions. Now we substitute the value of x equal to a, k2 is common, minus c e raised to power minus k2a plus d e raised to power k2a iota k1 f e raised to power iota k1a. So it is minus c e raised to power minus k2a plus d e raised to power k2a. It is equal to iota k1 upon k2 f e raised to power iota k1a. This is equation number 13. So now we have four equations. Equation number 10, 11, 12 and 13, and we will be solving these equations to get the coefficients a and b respectively. So now add equation number 11 and 13. So when we add these two equations 11 and 13, so first term c e raised to power minus k2a, it will cancel out. So it will be 2d e raised to power k2a and it will be 1 plus iota k1a upon k2 f e raised to power iota k1a. So d it will be equal to 1 plus iota k1 upon k2 f upon 2 e raised to power iota k1a e raised to power minus k2a. So this is equation number 14. Similarly, subtracting the equations, so here it will be 2c e raised to power minus k2a 1 minus iota k1 upon k2 f e raised to power iota k1a. So c will be equal to 1 minus iota k1 upon k2 f by 2 e raised to power iota k1a e raised to power plus k2a. So this is equation number 15. So substituting the values of c and d in equation number 10. Equation number 10 is a plus b c plus d. So from equation number 10, 14 and 15. So a plus b will be equal to c plus d. So it is one minus iota k1 upon k2 f by 2 e raised to power iota k1a e raised to power k2a plus 1 plus iota k1 upon k2 f by 2 e raised to power iota k1a e raised to power minus iota k2a. So a plus b it will be equal to from the first term we will get f e raised to power iota k1a, it will be e raised to power k2a plus e raised to power minus k2a divided by 2, then minus f e raised to power iota k1a iota k1 upon k2. This has common. Inside we will be having e raised to power k2a minus e raised to power minus k2a divided by 2. So this will be f e raised to power iota k1a. This is further common. This term it will be cos k2a minus iota k1 upon k2 sin k2a. So we mark this as equation number 16. Similarly, for value of a minus b from 12, 14 and 15, a minus b, it is equal to 12 number equation iota k2 upon k1 c minus d. So it is 1 minus iota k1 upon k2 f by 2 e raised to power iota k1a e raised to power plus k2a minus 1 plus iota k1 upon k2 f by 2 e raised to power iota k1a e raised to power minus k2a. So it will be minus iota k2 upon k1, and here the terms will be like f e raised to power iota k1a common. Inside it will be e raised to power k2a plus e raised to power minus it will be minus here k2a divided by 2 yes, and next term is minus iota k1 upon k2 f e raised to power iota k1a, it will be e raised to power k2a minus plus k2a divided by 2. So this is a simple mathematics. You can write the terms and take the things common. So f e raised to power iota k1a, this term it will be sin k2a minus iota k1 upon k2, this we have taken as common, this is cos k2a. So we take this term inside. So it is iota k2 upon k1 sin k2a, and this term will cancel out with this cos k2a. This is a minus b, and we mark this as equation number 17. So now we will be solving equations 16 and 17. So add 16 and 17, we will get the value of a. So it will be 2a. When I add the 2, this is common. So first is sin k2a common, k2 upon k1 minus iota k1 upon k2 plus 2 cos k2a. So a is equal to f e raised to power iota k1a, it is iota common, iota upon 2 sine hyperbolic k2a, k2 upon k1, k1 upon k2. This 2 here cancels out, cos k2a. This is equation number 18. So now subtract 16 and 17, we will get b. So it is minus f e raised to power iota k1a, iota k1 upon k2 sine k2a, k2 upon k1 sine k2a. So b is equal to iota common, f negative sign is already there, iota k1a divided by 2 k1 upon k2, k2 upon k1 sine k2a. So these are the values of coefficients, and from the wave functions we will be having incident wave function as a e raised to power iota k1x, reflected wave function as b e raised to power minus iota k1x, and transmitted wave function as f in the wave function 3 this. So now we will define the various coefficients. First is reflection coefficient. Capital R, it is defined as the ratio of reflected probability density current to the incident probability density current, and their values are, it is V1 psi star reflected part psi re, V1 because incident and reflected they lie in the same region, that's why we write here velocity is V1. V1 is the velocity of the particle in region 1. So here psi re, it is B star complex conjugate of psi re, it will be e raised to power plus iota k1x, e raised to power minus iota k1x, it is a star e raised to power minus k1x, a e raised to power plus iota k1x. These terms they will cancel out, so it will be b star b divided by a star a. So now we have values of coefficients a and b. We take their complex conjugates, substitute here, and we'll get the reflection coefficient. So capital R, it will be equal to b star. Value of b is here, we will take its star. So this is minus iota, it will become plus iota. Here minus iota, and rest will be the same. So it will be plus iota f by 2 e raised to power minus iota k1a, k1 upon k2 plus k2 upon k1 sine k2a. This is b star. B is minus iota f by 2 e raised to power plus iota k1a, k2 upon k1, k1 upon k2 sine k2a. Now we come to a star. A star can be found from equation number 18, f e raised to power minus iota k1a minus iota by 2 sine hyperbolic k2 by a, where is value of a? We will have to wait a bit. Yes, minus iota by 2 sine hyperbolic k2a, k2 by k1 minus k1 by k2, k2 by k1 minus k1 by k2 sine k2a. This is f e raised to power iota k1a, iota by 2 sine hyperbolic k2a, k2 by k1, k1 by k2 there is some problem, let me check. In the denominator we have to write this a star a, a star a, and here is a star iota by 2 sine k2a k plus cos k2a, and here it will be plus cos k2a plus cos k2a, and here it will be again plus cos k2a. So before writing you should check the terms carefully. So this f cancels, this f cancels, this cancels with this cancels with this. So in the denominator we are left with k1 upon k2 plus k2 upon k1 square sine square k2a 1 by 4, and in the denominator we are with a minus b a plus b, so it is cos square k2a a square minus b square. So minus b square is iota square divided by 4 sine square k2a, k2 upon k1, k1 upon k2 whole square, and iota square is minus 1, minus minus becomes plus. So reflection coefficient will be k1 upon k2, k2 upon k1 whole square sine square k2a divided by 4 cos square k2a, iota square is minus 1, minus minus becomes plus. So this is the required result, the reflection coefficient for a step potential in the tunneling concept. So now we will try to find the transmission coefficient. It is defined as transmitted probability density current divided by incident probability density current. So transmitted is region 3, and the region 3 is similar to region 1. So it is v1 velocity, it is the same velocity as in region 1. So v1 cancels. Transmitted part we represented it with f. So it is f star e raised to power minus iota k1x into f e raised to power plus iota k1x. Here a star e raised to power minus iota k1x, a e raised to power iota k1x. So these terms they will cancel out. So we are left with f star f divided by a star a, and here we substitute the value of a star a. So a star a values are, it is f star here, dear students, it should be f star and it should be f star, because f is complex conjugate, and when they cancel out, nothing f star will be found in the solution. So minus iota k1a cos k2a minus iota by 2 k2 by k1 minus k1 by k2 sin k2a into, this term is also in the denominator, this is a e raised to power iota k1a cos k2a plus iota by 2 k2 by k1 minus k1 by k2 sin k2a. So this f star cancels, this f cancels, this cancels with this. So transmission coefficient, here we are left with, in the denominator it is 1. So it is a minus b a plus b. So it will be cos square k2a. Iota square is minus 1. So it will be 1 by 4 k2 upon k1 minus k1 upon k2 square sin square k2a. So this is the probability for the transmission of the particle having energy E, and this is not equal to 0. So we say there is a finite probability for the transmission of the particle through a potential barrier in the form of a step, even when the energy of the particle is less than the step height. And this phenomena in which the particle goes through the potential barrier is called quantum mechanical tunneling. So quantum mechanics supports the penetration of the charged particle through the potential barrier. So this is all for today. Keep in touch for next lectures. Thanks a lot.